situation where a program is running but there's infinite waiting and there is no progress, or you have opened 10 different tabs and you're not able to perform any operation on it. What is that condition? Yes, that is deadlock. So explaining you deadlock in this video. So for example, let's forget about computers. There are two persons, person A and person B. Person A has a pen and person B has a notebook. Now person A having a pen is asking for notebook, and person B having a notebook is asking for pen, and it's not releasing its own notebook and pen. It's not releasing its own resources, and hence there is an infinite waiting time, and they are not releasing its own resources, and hence this is a circular wait condition where they're not releasing their own resources and still asking for the other resource, and hence this is deadlock. There is an infinite waiting condition. So there are four conditions that causes deadlock. Before making you understand that, you can map the same thing as this picture where these person are nothing but a thread, and they have allocated or acquired resource A and resource B respectively, and they're asking for resource B. Thread 1 is asking for resource B despite not releasing its own resource A, and thread 2 is asking for resource A despite not releasing its own resource B, and hence there is no progress and infinite wait condition, which is called deadlock. Right? These are the four conditions: mutual exclusion, hold and wait, no preemption, and circular wait, which causes deadlock. Mutual exclusion is that both thread A and thread B is working separately, excluded. They are mutually excluded. Hold and wait means thread A has uh, its own resource and it's not releasing that resource and still asking for thread B's resource. Hence, it's holding and waiting for the other resource and not releasing its own resource. No preemption means that nobody is ready to stop and nobody is ready to preempt the own process, and hence no preemption. And circular wait is something like this, where in a circular manner there is a waiting condition, and hence all these four conditions cause deadlock. And you must be wondering, I have heard of the terms like starvation, live lock. So what is the difference between deadlock, starvation and live lock? Deadlock is that these threads are permanently, indefinitely waiting for each other. And starvation is, like, for example, you must have gone in Bangalore traffic. You must have seen these bikes going, but the car still waiting and getting ignored. Or starvation is like one thread repeatedly gets ignored while others are getting the resources. Live lock is that threads are continuously reacting to each other, but there is no progress, right? So mutual exclusion, hold and wait, no preemption, circular wait causes deadlock, but the prevention is these three techniques, which is consistent lock ordering, small critical section, try lock or timeout. And to explain this, I will take you to another place which says locks. So you must have heard locks are used to prevent deadlock, and what and how exactly it is used. So lock is nothing, it protects the critical section. So for example, thread A and thread B or thread 1 or thread 2 share some code. There's some shared data that is called critical section, and you lock that, okay? uh, so basically lock is protecting that critical section so that multiple thread will not come and ask for the same shared data. Okay, so you use locks then, and lock is acquired critical section on the critical section, and then lock is released. Okay, so you can see this code, right? So in this code you can see these are the header files, and IO stream, input output stream, thread mutex, namespace std, and then you have mutex m. Account variable initializes 0, and in the void increment function you can see this lock guard mutex lock m. Lock guard is nothing but it follows RAII, which is resource acquisition is initialized. Basically, object is created and then automatically it is released. So lock and something shared data or some critical section code will be locked and then it will be unlocked based on the access. Whoever this thread wants access, then it will unlock. So it will be locked, but the shared data will be locked using log card. So automatically it creates and releases. Okay, whenever this goes out of scope, it will release. Okay, so then you can see what is mutex. Mutex is what something that is providing you mutual exclusion, right? So if thread 1 is acquiring critical section, then it will do everything and then release, and then till then thread 2 will wait, and then thread 2 will get its own turn. Okay, so only one thread can use mutex at a time. Okay, so see, this is how deadlock is happening, wherein you can see that thread 1 is locking A, it wants B, and thread 2 is locking B but wants A, and then there is this wait condition, and hence this causes deadlock. Okay, this lock card is RAI for creation and then releasing the mutex, right? So to prevent this, you can use scoped lock, which is basically if it goes out of scope, it will uh, it will remove deadlock, and that is caused by inconsistent lock ordering. So to remove deadlock, you can do consistent lock ordering, which means that thread 1 will have A, and thread 2 will also have A first. And if thread 1 is locking A, then locking B, it will work and then release, and then work will be done on thread 2. Till then it will wait for A, lock A, and then it will work. Okay, so basically you will do consistent lock ordering to remove the deadlock. Or you can use timeout like a timer, or you can basically use the scoped lock, or you can use or do small critical section or small shared data you keep, not big a big critical section, just small critical section. These three will prevent the deadlock. And if you want to avoid deadlock, okay, so for the deadlock avoidance, what we can do is we can do banker's algorithm, which is nothing but, for example, you are in a bank and bank has money, and there are customers that are coming in and they want money. So you will see, okay, how much they can actually a customer can actually acquire. For example, if a customer can only acquire 10 rupees, and so you can at max only give 10 rupees, and it has been allocated 5 rupees, so the need is 10 minus 5, that is maximum minus allocated, which is 5 rupees. 10 minus 5 is 5 rupees, so the need is 5 rupees, and I have to see what is available, how much resources are free, and then I have to see according to the available and the need. Okay, need is 5 and how much is available. For example, 3 is only available, and some request comes of asking 4, so I will say, okay, wait, let the 3 get completed, then maybe you can get. Or if the need was 5 and then they are asking for 7 as need, I'll say rejected, it will not work. But if it is asking for 4, then I will say okay, accepted. So available and need, both of them will tell me, okay, if the process is safe or not, right? So this will basically make a safe sequence, like this safe sequence. If you follow this safe sequence, there will be no deadlock, and hence deadlock will be avoided. You can see this is a resource request algorithm. It will see the need and available. Its request should be less than or equals to, otherwise it either will get rejected in need, and available it will wait. And need is basically maximum minus allocated, and safe state is safe sequence. And main purpose is like you have to enter in a state where deadlock uh, would not actually occur. You are in a safe sequence. So this is how you make these metrics. You see, this is available, this is allocated, this is maximum and needed. P0 to P4 are processes that are coming in, and you can see if I do max minus allocated, that is 7 minus 0 7, 5 minus 1 4, and 3 minus 0 3, I'll get need. And after I get need, I'll see, okay, I have uh, need, and this is a work, or this is a request that's coming in. It cannot be completed, no. P0 cannot complete. Okay, then I get need as 1 2 2. So can it be complete? Yes, this can complete because each of these are less than the need. 3 so then this 3, so P1 can get finished, right? You can finish this, so you will add this in allocated one, and then get the new sequence 5 3 3 5 new numbers 5 3 3 2. And then we will see why after P1 you can do directly P3, and then 5 3 3 2 you have, then you will see again, and like this you can make safe sequence, and this will prevent deadlock. Okay, and another concept which is asked a lot is, what is the difference between lock and semaphores? So this same critical section, lock or mutex, is just for one time, but if you have multiple threads that are coming up, you will use semaphore. And semaphore could be binary, which is 0 1, or could be counting semaphore, which has a variable like count. So for example, count is set to 3, so 3 threads can only process it. So like thread 1, thread 2, thread 3, only 3 thread or 3 people can only process that. Fourth person or fourth thread cannot process that. So that is count semaphore. Okay, and this is based on the critical section or shared data only. Lock for one single thing, and the semaphore when multiple threads are trying to access. And you can use binary 0 1, which is similar to locks, or counting, which has a count variable. And yeah, you can do that. So this is what lock is. It protects shared resources. Mutex, uh, mutual exclusion. One thread will own one lock at a time, and then this is a deadlock condition. And then prevention, you can do consistent lock ordering or use scoped lock. And I hope you understand deadlock now, and could explain it to anybody else too. Okay, bye. And one more thing is that semaphores can use signal or release also, like we had locks. Semaphore uses signal and release as well. So yeah, that's it. Thank you.